Okay, we're starting recording. Thanks, Steven, for showing us your code. We have yellow ducks in the background because we will be asking questions that we might want to ask, or because we are yellow ducks and we don't know anything. So we will not reveal whether we actually know or not. So what do we see in equation number 2?
Okay, so let's start here with the fundamentals of this technique, okay, which I think you guys might be familiar with, but for anyone else who watches this later, let's start right back at the beginning. So the idea here is that we want to find a way of approximately diagonalizing many-body Hamiltonians. Now, there are a lot of different ways that you can do this. One way that people might be familiar with is called a Schrieffer-Wolff transform. So the Schrieffer-Wolff transform is written here in equation 2. So I take my initial Hamiltonian H and I apply some unitary transform, this e to the s. I apply this to the Hamiltonian, and then I can expand these exponentials, and to leading order, I get something like this. I get the old Hamiltonian plus this commutator. S here is the generator of the unitary transform. I'm free to choose that to be pretty much whatever I like. And if I choose it carefully, I can make this commutator equal to the off-diagonal bits of the Hamiltonian. So the Hamiltonian minus the off-diagonal piece gives me, to leading order, a diagonal Hamiltonian. That's the idea. Except, of course, this is not exact because we have to Taylor expand these exponentials, and then you have a lot of high order terms hiding in this ... So this is one way to approximately diagonalize a Hamiltonian, but you have to have some way of guaranteeing that these neglected terms are small or are not going to cause you any problems. So what we want to do differently is we want to make a continuous unitary transform. The idea is, instead of doing one big unitary like a Schrieffer-Wolff, I want to make infinitely many infinitely small unitary transforms. So what we do is we introduce this new parameter L, which is called a flow time, such that L equals 0 is the original Hamiltonian of the problem, and L to infinity is hopefully a diagonal Hamiltonian. And we want to advance the Hamiltonian by small time steps dl. So we want to just apply lots of small transforms to go from L equals 0, the initial Hamiltonian, to L equals infinity, a diagonal Hamiltonian. So equation 3 shows you one of these infinitesimal transforms. So it's pretty similar to equation 2, except now the unitary has this dl in the exponent. Dl is infinitesimal. So when I expand these exponentials, it comes out exactly like this with no extra high order terms. Okay? And eta here is, at the moment, just some generator. We'll get into what that is later. So the point is that we can make these small, ideally infinitesimal unitary transforms, and we can do them all accurately with no high order terms causing problems. That's the idea. And in fact, you can just take derivatives of both sides here, and then you get equation 4, which is the flow equation. It's like an equation of motion for the Hamiltonian. It tells us how the Hamiltonian evolves under the action of this transform. And if you're familiar with the renormalization group, that's how I got into this. It's a bit like an RG equation for the Hamiltonian, where the fixed point is a diagonal Hamiltonian. That's the idea. So we want to solve the flow either numerically or in some cases analytically, reach this fixed point and obtain the diagonal Hamiltonian. And along the way, if we keep track of all of these infinitesimal unitaries, we also get the full unitary that diagonalizes the Hamiltonian, which allows you to compute various observables and switch between the initial basis and the diagonal basis. So that's the idea. For the generator, you can choose a lot of different things. You have quite a bit of freedom. Ideally, something that diagonalizes the Hamiltonian, and it has to be anti-Hermitian. But the choice that we use in this work is the generator, which is pretty common and quite numerically robust. The idea is that the generator is just a commutator of the diagonal part of the Hamiltonian, H naught, with the off-diagonal part, V.
I want to check something.
Yes.
On a tangential note, are you guys familiar with any flow based methods to find eigenvectors of a matrix?
You can find eigenvectors of a matrix using this method. It doesn't work so well. It doesn't work so well once we go into the interacting picture, but if you have a non-interacting system, or if you're working in the full exponentially large Hilbert space, you can do this. The idea is you solve the You solve the flow to get your diagonal Hamiltonian.
Mhm.
When you do this, you also obtain the unitary operator, or rather you obtain like the series of infinitesimal unitaries.
Right.
Then in the diagonal basis, you know what your eigenvectors are because they're just product states. And if you're working in like the full Hilbert space or with a non-interacting system, then the eigenvectors are all really simple. They're all zeros apart from one entry, which is a 1.
Yeah, and then we rotate them with the full unitary
Exactly,
to get the
exactly,
eigen.
yeah.
Okay, okay.
So to do this, you have to be either in the full main body Hilbert space, where your Hamiltonian is an exponentially large matrix, or you have to be working in the non-interacting system where it's just a linear matrix and it's quite simple to do. This doesn't translate quite so well to the tensor approach that I'm going to talk about here. You can do it. You can write down an expression for the many body eigenstates, but I'll show you later perhaps that it gets basically I don't know what to do with it. I can write down the expression, but it's almost certainly not written in an efficient way. So it's formally, yes, we can obtain the eigenvectors, but in practical terms, I don't think it's useful right now. That's something that I would really like to fix in the future. I'm sure there's got to be a smarter way of doing this.
Okay, thanks.
All right, so what was I saying? Yeah, so that's the game. We've got the flow equation in equation 4, we've got the generator in equation 5, and with this choice of generator, everything just comes down to computing commutators. So for some systems, you can work out the flow equations exactly, but this version, we want to do the whole thing numerically. Now, if you're working with a non-interacting system, or if you're working with, again, the Hamiltonian as a big matrix in Hilbert space, you can just compute all these commutators directly as matrix products. Was there a question?
So in PyFlow, did you follow this notation? So eta or some kind of namings like that will be important?
Yes. Yes. Yeah.
So I think one thing that you didn't mention, I think in your notation, H naught in equation 5 is, you say it below the diagonal, right?
Yeah. Yeah,
Okay.
exactly. It's
Yeah.
the diagonal part. So it's what you choose to be diagonal. So here for me, H naught is anything that is a product of number operators, and V is anything that has, C dagger I CGA type terms where a particle might move from one site to another.
One more question. Do you know of are there any integrable flows in this in the sense that it's an interacting system and still you can maybe solve the flow equation analytically maybe or something like this?
I mean, you can write down the flow analytically, but the problem is a bit like
No,
renormalization group. For a many body system, you generate higher order terms in the Hamiltonian, and I don't know of any system where you don't do this. So you always generate new high order terms, but the hope is that they're small.
Yes, so the generic behavior would be that there would be like a cloud of operators that you need to keep track of. And you say that you're not aware of anything magical thing like better ansatz for flow equations or something like this where
No,
yep,
unfortunately,
okay.
I'm not.
That was worth asking for me.
Yeah, I mean, the thing is, like, a lot of flow equation works use this Wegner generator, right? Because it's quite common, it's numerically stable, it has some nice properties, particularly if you're coming from a renormalization group background. The way this works is it removes couplings between sites that are very separated in single particle energies. Like the higher the single particle energy separation, the faster the couplings are removed. So it's got this kind of energy scale separation, a bit like renormalization group, where you start with high energy couplings and you work your way down to low energy ones. So there's a lot of historical reasons why people use this, but it's not necessarily the best for any given problem. And I think there's not been much work in finding better generators or alternative generators. So to answer that question, let's say if you know what all of your conserved quantities are, maybe there's a smarter way that you could write the generator in terms of the conserved quantities somehow, and then that would lead to a more controlled flow. This, I don't know. But I do think there's a lot of scope to build better generators.
It was a smarter answer than my question, but I think it's interesting that you say that maybe if I have integrability, maybe thinking in terms of those better constants of motion. Maybe that's interesting. So great that we're recording, because actually Kishore Bhatti was asking me precisely this question: how do you choose the best generator? So do you have like some methodology in PyFlow for selecting maybe a better edge node? Because as I understand, you could modify it, right?
You can, but in these types of systems, ultimately, I'm doing this in the context of MBL, right? So I want to get this sort of L-bit model. So the structure of my H naught is pretty much set by the structure that I expect to find, which is a product of number operators. In principle, you can choose H naught and V more or less freely. So you don't have to completely diagonalize the system. For example, you could pick V to be just one off-diagonal coupling and just remove one off-diagonal part. You know, you could decouple, let's say, a system from a bath or something like this, and then you get an off-diagonal Hamiltonian for your system and an off-diagonal Hamiltonian for the bath, but no coupling between them anymore, right? So you can play this game and you can sort of pick the generator and H naught and V freely to suit whatever problem that you're working with. And like I say, there are other choices of generator that are not based around commutators. There are other choices that are not so easy to implement in the way that I'm going to show here, but that have different properties. Like, for example, there's one called a Toda generator, which it worked for systems where the Wegner flow doesn't work, and it rearranges all the eigenvalues into ascending order, which mathematically is nice. And numerically, it's a nightmare because it's forever swapping all the eigenvalues around until they reach the correct ascending order. So, I mean, there are a lot of different choices of generator, and I think there's a lot more work to be done on finding good ones, to be honest.
All right. Okay. That answers my question, I think.
Okay, cool.
Thank you.
Yeah, it's actually kind of related to something that I wrote here. There was a work a few years ago on adaptive Schuffer-Wolf transforms, which was a way of adding in like the neglected high order terms from Schuffer-Wolf only when they're required, only when they're useful. You can you could play the same game here if you wanted to. For example, like, I write the flow equation like this in equation 3 as if it's exact, but obviously numerically DL is not infinitesimal, it's just some small number. You could imagine adding the high order terms in here if you wanted to. I've never found it useful, but in principle, maybe there are cases where it could be useful.
For quantum computing, for sure, I think, because you want longer steps, so you want to reach the more efficiency, maybe.
Yeah, that would make sense. Yeah.
Okay, great.
Cool. All right, so let's skip on to how we actually do this. So the difference, kind of the unique thing with this method, which we've been calling TensorFlow equations, is that we represent the running Hamiltonian in a kind of an unusual way. So let's take some generic fermionic Hamiltonian here. I want to write it as a two-body part, where here I could be equal to j. So this contains both diagonal and off-diagonal parts. And then I have this four-body part here, okay? And this encompasses a bunch of different Hamiltonians that you can think of, like just generic interacting fermions or whatever you like. But under the action of the flow, you tend to generate new off-diagonal terms at early stages in the flow. So even if you start with some like sparse Hamiltonian, very early on in the flow, it will just take this completely general form where you have a bunch of off-diagonal terms and it looks something like this. And then later in the flow, it will converge back towards something that is diagonal. So the point is, I want to represent my Hamiltonian like this, and then I want to represent it diagrammatically like this thing here on the next page. So I want to say that this two-body part of the Hamiltonian is, the two-body part of the Hamiltonian is a matrix, basically, an array with two indices. And the four-body part of the Hamiltonian is rank 4 tensor, so an array with 4 indices. So here we are.
So PyFlow uses rank 2 and rank 4, which means that you never consider maybe 6 operators, right?
I do consider up to 6 in PyFlow. But
okay.
It gets a lot slower, and I've not found a system where it's really very useful yet.
Perfect.
It depends. Okay. I guess it depends on things like interaction strength. So I'm working with relatively weak interactions, and maybe you'll see later if it's in here why this matters. But yeah, the idea is that I want to represent the Hamiltonian like this. So to completely abuse notation, it's a matrix plus a tensor. That's how I want to store this in computer memory. And ultimately, my final diagonal Hamiltonian should look something like this. Okay, so it's just sums of products of number operators. The tilde here means we're in the diagonal basis. And then my final diagonal Hamiltonian should look like this. It's still a matrix plus a tensor, but here both of these indices are equal, and same deal here, right? That's my diagonal tensor form. So this means that when I'm working out things like the commutator of H naught with V for the generator here, I can split this into the two body terms and the commutator of 4 with 2, 2 with 4, and then high order terms. And then this is where the approximation comes in, because I've neglected the commutator between two fourth order terms here. And the idea here is if the interactions are weak, then anything that has a product of two fourth order terms should be also very weak and should be negligible. So that's why I want to just restrict myself here to this form where it's a rank 2 plus a rank 4 array and then not include the higher ones.
Okay, yeah, everything great. One yellow duck question. Is there a way to ensure that if you will drop those higher order terms, that this is still a unitary transformation?
Yes, so there are, well, I don't know about ensure, but at the end you can go back and you can check, because unitary transforms have to conserve certain properties, right? So for one thing, they conserve the eigenvalues of your problem, but more generally, they have to conserve traces of integer powers of the Hamiltonian. So what you can do is you can compute this at the beginning of the flow and then again at the end of the flow and compare them and see, are they still equal to each other? And there are a couple of ways you can do this. For simple systems, you can do this analytically, or what you can do is just build the Hamiltonian as a full matrix, but just in some subspace of the Hilbert space. Let's say just the part of the Hilbert space where I have only two particles. And that way I can still build the Hamiltonian for quite large systems. If you have at least two particles, then you still have some non-trivial interactions, so you can still measure whether these interaction terms are conserved or not. So yeah, you can use it, they're called flow invariants. You can compute these flow invariants as a self-consistent measure of whether the transform is still unitary or not. And of course, in general, because you're neglecting terms, it won't be perfectly unitary, but you can put a number on how unitary it is. And for most of what I'm showing you here, it's unitary to, I think, well within 1%. These quantities are conserved to within 1%.
All right, I see. So basically in PyFlow, equation number 9 will be important because there will be a truncation and that will lead in practice up to maybe 1%, some deviations. Yeah. And PyFlow does this kind of Cayley-Hamilton invariants and so on, like those kind of trace invariants, or you would have to do by hand?
At the moment, I'm doing them by hand. I think the current public version has a computation of a flow invariant, but I'm not sure that it's actually correct, so I don't use the built-in version right now.
Perfect. Okay, thanks.
So yeah, so we can compute these commutators, and then the next bit of this paper just goes through how to compute them. So if you take the quadratic part, H and V are just matrices. You can do this one by hand if you want, or you can do it in this graphical notation. And then the simplification here is that in the graphical notation, these commutators are just sums of tensor contractions. So all I'm doing here is just contracting one of the indices here, setting both these indices equal to each other, and then summing over k, summing over the repeated index. For the quadratic case, it's relatively simple to do this by hand, and then you can check that the graphical notation gives you the same thing. It gets a bit more interesting when you're looking at these higher order commutators. So you can do this by hand for the commutator of a 4 with a 2 if you want to. Looks like this. It's pretty complicated. You know, if you look at this, I'm not sure if you can see much of a pattern unless you really stare at it for a few minutes. But if you write it graphically, it's just the sum of all single particle contractions. This is the kind of nice simplification with this graphical notation that allows us to make a bit more progress. I should also say that I'm using a thing here called vacuum normal ordering, which means I am rearranging all the operators in the Hamiltonian such that the dagger operators are on the left-hand side and the non-dagger operators are on the right-hand side. If you don't do this, there will be additional terms in equation 11 corresponding just to rearranging operators around. So I'm taking a slightly simpler form here, but in general, then
And the ordering,
yeah,
how does it look in the diagrams?
in the diagrams, what happens is the additional terms that you would have would be 2-point contractions, like 2 or 3-point
Ah.
contractions. So that's why I'm ignoring them
Yeah.
for the moment.
Right.
Just because if you normal order by hand first, then the linear algebra is a little bit easier. Also, if you do 2-point contractions, strictly speaking, there's an expectation value with respect to some reference state that starts to appear. And this is a bit harder to compute. You have to pick a reference state, which normally people will choose to be the ground state, or you can pick it to be like a finite temperature ground state if you like. Here, my reference state is the vacuum, which means that all the higher order corrections just vanish. So that corresponds to what I just said, vacuum normal ordering, where I just move all the Dagger operators to the left. For me, it's more of a like a technical trick. It's just a way of making sure that my operators are always ordered in a consistent way. Because if you have the full freedom just to rearrange fermionic operators as you like, then it just becomes super messy. It's really hard to say what comes from a fourth order term, what comes from a second order term, because if you just permute the operators around, then you can generate new terms and it just gets really, really messy. So for me, I vacuum normal order everything, which is actually the reason why in an earlier Hamiltonian up here, I use these this sort of colon notation here. These colons mean vacuum normal ordering.
Okay. Right.
Okay, so the idea is that, yeah, we can represent all these commutators efficiently just as tensor contractions, which means we can compute this, on a modern computer quite efficiently, particularly on things like GPUs, graphics cards, where you have a large number of cores and you can parallelize this problem quite effectively because it just boils down to doing a lot of linear algebra operations. So it's really, really well suited to like big clusters or GPUs, which is what we use in this work. So the idea is that you compute all these tensor contractions, you then have to just rearrange all the indices into the correct order. So here you use your fermionic commutation relations and watch for your minus signs, rearrange everything into the correct order, and then you end up with the resulting single tensor that represents the update to the Hamiltonian or the update to the generator.
So the leg dimensions are actually the system size dimension, right? So it's relatively low tensor rank because it's 4. It's not like an MES where the rank of the tensor is kind of scaling with the system.
Yeah. So it's each one of these indices runs from 1 to n, if you like, where n is my system size. So I have 4 different dimensions, and each dimension is equal to the system size.
But then still, if you have this tensor representation after you did the minus signs correctly and so on, then you can directly run on GPUs, right? Because otherwise you would have to do similar linear algebra nonetheless, and keep track of everything with your updates, right? As you would be flowing, right? So basically, one thing that we see from this is it true that because of that you can use those fancy GPU packages, or that there's something more that is coming compared to just like a brute force NumPy representation of such a tensor?
I mean, you can do this in brute force NumPy if you like, but the benefit of using a GPU is that these problems can be parallelized really efficiently. Because I mean, what is a tensor contraction, right? You're just summing over all the entries where your 2 indices are equal to each other. This is something that can be done in parallel really, really efficiently, and you can do this in NumPy. I think that's what's done in the PyFlow tutorial. You can do this in NumPy, but a normal computer has, I don't know what, maybe 8 to 12 CPU cores, something like that. A cluster maybe has on the order of 100. A GPU has maybe 10,000 cores. So when you're working with really large tensors, it's quite helpful to be able to split these tensor contractions into 10,000 small operations, have them all proceed simultaneously, and then add the result all back together at the end. So for very small systems, you don't gain anything for running on a GPU. In fact, for a system of less than maybe 10 sites, I think it's slower to run on a GPU. But once you get up to 20 sites, 30, 40, 50, then GPUs become orders of magnitude faster than running it on a CPU.
So if I would have a GPU on my regular laptop and just my regular like processor on the laptop with like 8 cores, can you say like how much faster it will be on such a system size 50 or something like this? So
Depends
yeah.
on, I think, the GPU that you have, because there are some good GPUs by NVIDIA, like
Yes.
RTX something, which have large memories, then they can give you some significant speed up. But if you have like a bad GPU like me, like 2 GB, NVIDIA, some 1050 something, then you won't get
Yeah.
much
Yeah,
speed improvement.
this comparison to Figure 12 was run, I think, on a GTX 1660. This was on my own laptop a couple of years ago. Now I have access to some of the RTX cards, which I've been using to do the actual computations. But version 1 of this paper, we did everything on CPU except Figure to make the point I thought this would run faster on GPUs. Then I moved to Berlin and then I got access to a GPU cluster. So version 2 of the paper, there was a small bug in version 1. I had to rerun a lot of the data. So I reran it all on GPUs at this point. So now all the rest of the data is done on GPUs. And yeah, you can see they become a lot faster when you go to larger system sizes. But for small systems, small tests, they're pretty equivalent to each other.
So it's like 2 hours to diagonalize on the CPU and maybe a dozen minutes on the GPU, yeah?
Yeah, something like that. Although, as I say, this version was a much older version of the code, and the new ones are a lot faster and a lot more efficient. So I wouldn't pay too much attention to the absolute numbers there, but just more like the ratio of them.
Yeah, I just
GPUs much,
wanted
much
to get
faster.
some idea, like, given some sizes of the tensor. So on 50 sites, this is roughly like 50 to power 4, which is already like 10,000 sites, right? 10,000
Yeah, something
entries.
like that. Something like that, yeah.
Okay, then this is quite huge. Yeah, I see.
Yeah.
Okay, thank you.
So I think at the moment it can do I think a 12 site system, it can do in under a minute. 16 sites is something like 5 minutes. And then, yeah, by the time you start pushing what you can do with exact diagonalization on a regular computer, like maybe 18 sites, the flow equations start to become slightly faster than ED, certainly faster than just doing this all on CPUs. Okay, so that's basically that's the point. We just kind of repeat this trick again and again. We're computing these commutators. They're just sums of all the tensor contractions, and then we just use our fermionic commutation relations, make sure everything's in the correct order, add everything back together to compute. In this case, the generator. You play the same game again for the Hamiltonian. So in practice, we just reuse literally all the same code. We just send 2 different matrices and tensors to it now. And then we numerically integrate the flow equation using, here it's use the JAX library, so it's just an ODE solver. You could just do this naively and just say, well, the update to the Hamiltonian is DL times this whole thing, and then make some small choice of DL. That works, but you get an error that's something like order DL squared, if I remember right. So we actually use some sort of like Runge-Kutta 4th order, 5th order adaptive integrator here. So the integration error is like DL to the 5. So the integration error is much, much smaller than this truncation error. In the end, these neglected terms are the biggest error that we encounter in this procedure. Yeah, the neglected terms basically are proportional to the interaction strength, or to powers of the interaction strength. So as long as your interaction strength is much less than 1, the leading neglected term is something like order interactions squared. The next one will be interactions cubed, and so on. So if we have weak interactions, this truncation is reliable. When the interactions start to get more like order 1, and these terms they're still quite small, but it's harder to say anything rigorous about them. So for this stuff, I always work with weak interactions where I can be pretty confident these terms are negligible.
So like in the previous page, you have mentioned that, the advantage of using the TensorFlow notation is to, that it becomes easier to, is it on the previous page, or I read it? Yes, just below the big diagram. Here we can start to see why the tensor notation is useful. So thing is, these contractions, like if you write them as matrices, you know which index to contract as well, right? So, because numerically, even tensors are represented by, like, let's say 3D matrices or higher order like that. So I'm thinking, is it the GPU that's providing the advantage, or it's something about the notation itself?
For me, it's the notation. This is the relatively simple case where I'm not showing these higher order corrections. So I guess in the simple case, you can argue, is it really much better than just writing this thing down by hand? In more complicated cases, where I'm not using vacuum normal ordering and I have to normal order with respect to some chosen reference state, then I have these like 2-point contractions and 3-point contractions and so on. Trying to do the algebra, it's an absolute mess, and you can have like hundreds of terms and it gets really crazy. So for those more kind of sophisticated calculations, I find this notation much easier. Yeah, I always find it quicker. I have checked most of this by hand by going through all the algebra by hand to make sure that it gives the same results. So yeah, in the present case, you could argue that you can still do these calculations by hand, but I find the graphical stuff much faster. And even when I'm coding it or when I'm debugging it, if I have this picture in my head, I find it just much quicker. But maybe that's a personal thing. Maybe other people would prefer just to go through like all the equations by hand. For me, I find this notation easier.
And then it probably really matters for the solver ahead to also simplify as much as possible. So you mentioned this normal ordering and dropping some terms. Because if I wouldn't do that and maybe I don't need them, then my final tensor might be a bit bigger or something like this.
It's not that it'll be bigger, it's more that so normal ordering is just a way of making sure that we have a consistent ordering of terms. So if you take this equation 25, let's say I have some term from my fourth order tensor. I could rearrange this, right? I can swap j with k, and then I get this expression on the right hand side. And then I have a fourth order piece and a second order piece. And it's important just to pick a consistent order and stick with it, because if I'm being inconsistent, then some of my contractions will always be fourth order, some of them will be fourth order plus second order. And then it's not maybe wrong to do this, but it's, I don't know, it's messy, it's hard to keep track of. It just leads to strange behavior if you're not careful. So for me, normal ordering is just a way of making sure that I do something consistent. So there's a ton of maths and normal ordering here. For example, like this thing in equation 34, this is the commutator of two normal order terms, a fourth order term and a second order term. These G's are contractions, they should be written somewhere above. Yeah, they're just this, right? It's just an expectation value in some reference state. The tilde means the dagger operator is on the right and the no tilde dagger operator is on the left. So if you compute, let's say, a commutator of a fourth order with a second order term, you get something like this analytically. Now, the sum of a g with a g tilde is a delta function. So actually, the first two lines of this give you exactly what I was showing you on the previous page, where you just have the sum of all four one-point contractions. But then you also end up with these other terms here, which analytically, I don't know, maybe if you look long enough, you'll start to see a pattern here. But in the graphical notation, these are like 2-point contractions. So here I contract alpha with nu, beta with mu, and so on.
Yeah.
The catch is that these contractions also come with an expectation value. They're not just a delta function anymore. It's a delta function times an expectation value, and you need to pick the states for the expectation value. So one of the conventional choices would be the vacuum state, in which case all these terms vanish, which is what I'm using in this work. But as I say, you don't have to choose the vacuum state. You could choose any state that you want. And then in that case, you need to include these terms. And analytically, I find this really messy. But with the graphical notation, it's much quicker and much easier.
Yeah, I think I see more, because I also realized that that becomes problematic for quartic terms, the manipulations, and then I think there the diagrams would be easier.
Yeah, it very much does. I'm just wondering if I have the results for the quartic terms somewhere. Let me just try and find that. We never published the results for the quartic terms like analytically anywhere because the expression is so long. I don't think any journal would actually let us let us include it, but we have it somewhere. Let me just try and find it. I think uh, I think I'm sharing a window here, right? So if I drag a PDF onto that, you guys can't see it. Is that right?
So we still see the PDF viewer.
Yeah. Okay, so if I just pull up this PDF, this is something I did years ago. So be careful for typos. I can't promise you it's 100% accurate, but this is what I just showed you here. It's the normal ordering and then the commutator for quadratic parts, commutator for rank 4 with a rank 2. This is the commutator for two fourth order terms. It's a mess. And there is, I tell you what, homework exercise, there is one typo in here that I know of. So try and track that down if you really want to. But I found it because I did this graphically instead and I compared the answers. So it's grouped here. This first block are all the 1-point contractions that give delta functions. The second block are all the 2-point contractions that I'm allowed to make. This one is all the 3-point contractions, so you can see there are 3 G's here. And this block is all the 4-point contractions, which in the end just gives me a constant, so I don't need to care about this. And in the work that I'm doing here, if I remember right, it's the G, is it the G operators? Either the G or the G tilde are equal to 0. So in the work that I'm talking about here, actually, I think all of this or almost all of this vanishes. All this vanishes. Which makes our lives a lot simpler. But if I were doing this in full generality, I would need to include all these extra terms. And these are the ones that are made much, much simpler by the graphical notation. So I did this actually, the work I was talking about at APS March. This is what I did there. I was normal ordering with respect to an arbitrary excited state so that I could get non-perturbative corrections that would be appropriate to MBM. But computationally, it gets really heavy. And like I said, the real trick is that these things are no longer just delta functions, they're expectation values, and you do have to define a particular state. So if you pick the vacuum state, which is the conventional choice, you just get these leading order terms, and it's much, much easier to deal with. So you can check Kirine's book, for example. He goes into like a lot of detail about what these corrections do, how large they are, when they're negligible, when they're not, all that kind of stuff. That's all in there. But for me, I'm just using right now the first block here because I'm using vacuum normal ordering.
All right, all right.
Is the PDF that you show, is it a book?
Okay, so this one, no, this one is my old notes.
Okay.
From
I
my
thought-
first postdoc years ago. So yeah, I did all that by hand. Yeah, but Kirine's book, Stefan Kirine's book, is a really good resource for this. He doesn't show the ones that are this high order, but he does go through all these lower order ones and explain, the algebra in a lot more detail. But yeah, so that's fundamentally that's the building block of the technique, right? It comes down to just computing all these commutators by tensor contractions and then numerically integrating the final result with some kind of fourth order Runge-Kutta style integrator. And then once you've done that, you just repeat this procedure until the Hamiltonian converges. So yeah, that's what this section of the paper does. It just goes through the bullet points, which are basically already said. You build your Hamiltonian as essentially a matrix plus a tensor in the computer memory. You compute the generator by computing all these tensor contractions. You then compute the right-hand side of the flow equation by computing another set of tensor contractions. You numerically integrate by one time step from L to L plus, and then you just repeat this until the Hamiltonian converges to some desired accuracy. And then you pick, I think in this work we've set a threshold here for when the couplings decay to less than 10 minus u, we say the Hamiltonian is effectively diagonalized. And in this work, actually, we do store the full unitary. I forgot this. So when I say we integrate from L to L plus DL, you maybe apply the three unitary transforms to diagonalize the Hamiltonian. And in this particular work, I actually store them all so that I can invert the unitary if I need to. In more recent work, we've stopped doing this because it gets really intensive, right? Because if you've got 10 to the 3 flow steps times something in order L to the 4, you work this out yourself, the memory requirements become very quick, very fast. And in this work, it's actually the memory requirements is much more we can store on an individual GPU. So what we actually do, or maybe not in this work, but in one of the other works I've done, we actually compute the diagonalization in kind of chunks. We compute as much as we can on GPU, and we move that data onto system memory and save it. And then we do like another few hundred unitaries, and we move that onto system memory, and then we just keep doing it piece, which is quite cumbersome, and it can become quite slow to transfer data from GPU to system memory and back again. So ideally, you want to do it all on one big GPU if possible. Yeah, this was just a section on these flow invariants that you asked about. So, it's unitary, so it has to conserve traces of integer powers of the Hamiltonian. We use the second invariant, so trace of Hamiltonian squared. We compute that at the beginning, we compute it at the end, we normalize, and ideally this quantity should be close to 0, which says that these variants are well conserved by the flow. So that's our like self-consistent error estimate. You can also compare with other methods, right? You can compare with ED for small systems, and play all these kind of games to make sure that it's working accurately. But when you're working with very large systems, then you need some kind of self-consistent error estimate, and this is the way that we're doing it at the moment. We're also working on some slightly more rigorous error bounds so that we can say with a bit more precisely what sort of error we expect and when we expect it to be a problem. But right now, as a kind of good rule of thumb, this thing works very well. So yeah, that's pretty much how the technique works. And then if I just come over to the
so then maybe later we can ask you like at individual steps. So for example, equation 14 and stuff like this, maybe this is in PyFlow and so on. So you said maybe this not exactly, but maybe we can ask you later about PyFlow.
Yeah,
Okay.
yeah. I mean, we can jump over and talk
Great.
about PyFlow now if you like, because that's all the kind of fundamental stuff. The rest of the paper is just numerical results for quasi-periodic systems.
Perfect.
Which is, good fun. I think it's very interesting, but maybe not what we want to focus on here. So yeah, if we come over to the numerics, I'll briefly go through the non-interacting case because that stuff is pretty simple. But I wrote this notebook while I was introducing some of my colleagues here to the method. So you can download it. It's on GitHub. You can download it and go through it and check it all yourself. But the basic idea was that I just wanted to start off by diagonalizing some non-interacting system and Anderson model, which I can just build as a matrix. Here it looks like this. It's a tridiagonal matrix, a sparse matrix with disorder on the diagonal. It's very, very small here, just so you can illustrate it and fit it on a screen. And you can exactly diagonalize it in NumPy pretty straightforwardly. And then I walk through how to do this with flow equations. So exactly as I mentioned before, here we just do this in the most approximate way first. We just say the new Hamiltonian is the old one plus DL times this commutator. We work out these commutators just as matrix products. So eta as the generator is there, the updated Hamiltonian is there, the update step is there. And then we just repeat this in a loop until the procedure converges. The results from the flow and the exact method are here. There's a small relative error just because I'm doing the integration in a really kind of naive, stupid way. I can repeat this here with a better integrator now with the fourth order Runge-Kutta. And now you can see that I can get the exact results and the flow equation results to agree pretty well to many decimal places. And this is what the flow of a non-interacting Hamiltonian actually looks like. So a little bit hard to see, but the filled circles are the flow of the diagonal parts and the crosses are the flow of the off-diagonal parts. So the off-diagonal parts decay pretty quickly to 0, and the diagonal parts pretty quickly reach their final eigenvalues. And the point is that this is Wegner flow, so it's very smooth, it's very well controlled. There's no kind of discontinuity, there's no jumps. Everything is just really nice and well behaved, and that's a feature of Wegner flow. Other choices of generator tend to give kind of noisier flows and maybe require like very fine integration grids, but this one is quite robust. And in fact, you can see actually the grid of points I used here in flow time is logarithmic because most of the changes happen at very short flow times. And at the end, you know, nothing is changing. So I was able to pick quite a widely spaced grid here. And maybe you look at these and you think they're super far apart. How can this be accurate? The SciPy integration routine does add intermediate steps to check for accuracy. So formally, it adds additional steps in here when it's doing the integration, but I only saved the steps on a logarithmic grid because there's no point in having hundreds of data points up here because nothing's changing. The interesting system may be a bit more interesting. It takes the form that I showed you before. So here we're looking for interacting fermions. So disordered on-site potential, nearest neighbor hopping, and then a nearest neighbor interaction term. And the idea is we want to obtain this kind of L-bit Hamiltonian, which should look something like this. It's just sums of products of number operators. This is all the normal ordering stuff that I just went through. In fact, I think it's copied directly from the paper. So that's all the normal ordering stuff. And then, yeah, this is numerically speaking how we do it. This is not maybe the fastest way, but it's relatively transparent and easy to understand. So I'm using this NumPy einsum function to compute all of these tensor contractions. The idea with einsum is it's the Einstein summation convention. So if I give this function two arrays, so here a rank 4 array and here a rank 2 array, then it will sum over any repeated indices. So here's the index D, and then it returns me a rank 4 array with the indices in some order. So this function here, which is called com, is doing the tensor contractions here. For in the first case, if it's two matrices, in this case, if it's a rank 4 with a rank 2, and then in this case, a rank 2 with a rank 4, but I've swapped the order just to reuse the above code. So I don't claim that any of this code is the most efficient way of doing it, but this was just a kind of pedagogical way of showing how the method works so that people can read this and hopefully understand the steps involved. So that's kind of the core of the method is this function.
Yeah.
So it's paralleling the tensor boxes that you were showing, right? So for each of the diagrams.
Yeah, exactly. That's what it's doing.
And then if I wanted to check that you did it correctly, I would have to check where the contraction goes, and then you those arrows are saying what goes with what, yeah?
Yeah.
Okay.
But you would have to first calculate these, like which index is being contracted to which one, like on paper, and then you just map it to the like NumPy language syntax.
Yeah. But the advantage of the graphical notation is that I know that it's just the sum of all the one-point contractions. So for example, here, I know that I have to contract this annihilation operator with this creation, and there should be one that contracts this annihilation operator with that creation, which is, where is it here? This one.
Right.
Yeah, so for example, and then I rearrange the operators in the end. So this F was at the end, it has to hop over the D and the C, and then it becomes here. Yeah, so if I know that I have this structure, then I find it much easier to see that I'm doing all the contractions correctly. But you're right, you can do it all by hand, by paper, like algebraically, or you can work it out with just the boxes and drawing the arrows. Yeah, you can do it either way, whichever makes most sense. And then, yeah, so this was like the core of the code here, at least in this pedagogical code. It's this, which I'm just doing on NumPy, all on the CPU here. The actual integration is done by this slightly more complicated looking thing. This just is where I kind of split the Hamiltonian into quartic and quadratic parts. I'm sort of picking out the diagonal and the off-diagonal terms here for the quadratic part, here in slightly more lengthy way for the quartic part. And then, yeah, I'm just calling this function com to compute the commutator between all these different pieces. So my notation here is not super helpful. H naught is actually a second order piece and V int is a fourth order piece. But At some point, I will go back over this and give everything a 2 and a 4 just to make it clear what's what. But yeah, essentially, this is the step that does the integration by one time step. And then down here, I have a bit of code that just runs through the whole procedure for a small interacting system, and then it computes the eigenvalues and compares them with ED. So this little block here is just doing ED, and this little block is doing the plot. So at the end of the day, we get the eigenvalues from the flow equations in a blue line, ED in the orange line. They agree pretty well, and then you can compute the relative error, which is less than 1% here. So all the above code is just kind of going through the steps of computing this stuff. It's doing exactly what I already said. There's nothing new in there. It's just doing it in a bit more technical detail. And yeah, once you've done this, you've got your diagonal Hamiltonian, so you can compute various different things with it. What we're actually doing here is, where's my Hamiltonian gone? What we're doing here is we wanted to compute this L-bit form. And in MBL, the kind of folklore is that this term, this delta ij, should decay exponentially with distance. So it should be, e to the minus absolute value of I minus j or some length scale. So once we've diagonalized the Hamiltonian, we've actually constructed this thing, so we can look at it, we can extract it numerically and see how it works. That's what we do down here. After the eigenvalues, we compute the L-bit interactions. So this is delta ij with distance I minus j on a log scale. It's for one disorder realization in a very small system. So if you're being very nice to me, you could say that this is an exponential decay. But you'll find if you go to larger system sizes, or if you do disorder averaging, then this does end up giving you a nice exponential decay and becomes a straight line. So that's kind of what we were doing in this work, where I wrote this notebook for it. There's also some other stuff I was doing here with transforming number operators, which is maybe a bit more relevant to the kind of Lieb-Robinson bounds that we were talking about. So you can also transform any local operator from the diagonal basis to the initial basis, or vice versa. It doesn't really matter which direction you go in. The quasi-locality properties are pretty much the same. They're not identical, but you can make an argument that if a unitary is quasi-local, its inverse is also approximately quasi-local with the same locality properties. So everything I'm doing here involves computing an L-bit correctly. So like starting from a local object in the diagonal basis and bringing it back into the original basis. We've recently found it's much more efficient to do the opposite. We start with a number operator and we just take it into the diagonal basis. They look almost identical to each other, and they have almost all the same properties. The catch is if you're doing the reverse unitary, you need to store the entire unitary in computer memory, which is kind of a mess. But if you just do the forward integration, you don't need to store the unitary, so it's much more efficient on the memory. But anyway, that's a technical aside. The point is that if you start from any local operator and you transform it in the same way, it takes this kind of really complicated looking form. So entailed here would be initially just a local operator defined on one lattice site I, and under the action of the flow, it becomes this thing. So it becomes non-local, becomes off diagonal, and it acquires these higher order terms because of the interacting part of the Hamiltonian. So yeah, this should also be normal ordered. There should be colons in here, but I think I just dropped the normal ordering at some point just to make the notation cleaner. But yeah, all of this is the same. It all comes back to computing these same commutators. N is also stored as, again, like a matrix for the first two parts and then a tensor for the later parts. Pretty much it's transformed with all the same code as before. In fact, this is almost exactly the same code as before. I just added 2 extra lines here to compute the flow of the L-bit, as well as the flow of the Hamiltonian itself. So then you just run through all the same things as before, same numerical integration as before, and you can plot the various components of the L-bits. So here was the alpha, that was the quadratic part. Here was the gamma, which was the quartic part. This L-bit was, I think, centered around site 3, so the quadratic part decays roughly exponentially as you go away from site 3. Here I'm showing this against I minus j. So again, this should be an exponential decay, just a straight line. It's a very small system and it's only one disorder realization, so it's not. There's some noise in here. But the idea is we can diagonalize a Hamiltonian and we can compute all these local operators. This was some stuff looking for a phase transition, so that's maybe not so important for what we're doing at the moment. And yeah, the notebook just with one big function that just does everything that was discussed above. So then you can put this big function into a loop and do some disorder averaging. This part was me trying to define some slightly faster functions. So above I used NumPy's einsum. Einsum is pretty good, but if you have a specific task in mind, you can do a bit better. So here I'm using generalized universal functions here that are, I find, quite a lot faster on the CPU. That's just a technical detail. It's doing exactly the same as the NumPy functions, just quicker.
On the CPU or GPU?
Here, CPU.
CPU, okay.
Yeah.
And the idea is that somehow, because it's like rank 4, you can just make it explicit and then it goes, or?
I mean, the idea here was just I'm working with small systems and I wanted to keep it quite pedagogical, so I just wanted some way of
Okay.
doing this. The thing with
Fine,
what
yeah.
makes it fast is that if you're using numbers GU vectorized stuff, you can type declare like you would do in C or something, right? NumPy's einsum doesn't do type declarations, so it's quite slow. It has to allow for the possibility that you're trying to add, you know, a float to an integer or multiply it by a string or whatever. If you're working with GU vectorized, you can type declare, and if the compiler knows that everything is going to be 64-bit floating points, it can run a lot more efficiently. So that's all that's happening in here. I just redefined some functions that are a little bit faster. They're still not as fast as a GPU for big systems, but yeah, faster than the NumPy functions above, but a little bit less transparent, less easy to see what's going on, I think. Yeah. Also, you can start to see the computational problem with this is that actually there's like a whole bunch of nested for loops, which this is why it's kind of painful on CPUs. Nested for loops are never really a good idea, but you can't avoid them here. So if you can parallelize these loops, then it will run a lot faster. That's why GPUs are useful. But yeah, so that just kind of redefines all the functions in a more efficient way. And then here I'm calling the functions that I've defined above for, I think this is the case of Van A Stark potential, just as an example. So we can compute like L-bit interactions or quadratic parts of the L-bits and so on. And just compute it all in a kind of nice way for different. Here, this looks like a disorder strength, but it's Van A Stark. So Van A Stark is a linear potential with a gradient W. So the larger the gradient gets, the more localized the system should be. So yeah, this lets us compute all the parts of the L-bits themselves. This is the interaction term of the Hamiltonian. This bottom figure is a transformed L-bit operator in real space. So you can see the real space support of the L-bits. And then yeah, you can compute things like relative error, comparing the eigenvalues against ED. There's a kind of weird spike here. I don't know why that is, but you can see the numbers are all pretty small. So the relative error here in the eigenvalues is very small. And this was estimating a phase transition, so I'll skip that. That's not really important for what we're talking about. But yeah, this is kind of the point. You run all this code, you get the diagonal Hamiltonian, you can extract the L-bit interactions, and then you can play the same game. You can transform any of the operators as well. Once you've got the diagonal Hamiltonian, you can also time evolve relatively straightforwardly, right? In the diagonal basis, time evolution is pretty much just multiplication by a phase. So if you've got everything in the diagonal basis, you can work out the time evolved operators. And then if you want to compute expectation values, maybe you have to come back into the microscopic basis again. Depends what you're doing. If you're computing like infinite temperature traces, you can do it in the diagonal basis. Yeah, at this point, you can kind of do whatever you like, but that's the procedure. That's the fundamental details of how it works, and then some of the technical steps and how it works. And you can download this Jupyter notebook and run through it and yeah, play with it yourselves and apply it to different problems, check it works, all that kind of stuff.
All right, perfect. Thanks for the overview. Can you comment on, so you made it quite explicit here, but as I understand, PyFlow is also like a bit of a package. So is this taken from code bytes in PyFlow, or? can you maybe comment on the code structure?
Yeah, so PyFlow itself is a bit more sophisticated, it can do some more things than that could. PyFlow is, I will admit, it's not very user friendly right now. The main function is just there's a main.py, which is the thing you probably want to use. It's set up right now for interacting fermionic systems, and yeah, basically you can just call it in a relatively simple way. Here you call main py, you tell it the system size, you tell it the type of potential you want to use. Here it's random, and you tell it what contraction routine to use. There's a bunch of different options. Einsam, tensor.vec. I think I added Python recently, which is quite a fast one. So this version of it runs mostly just on the CPU. And yeah, there's a whole bunch of things that I'm still working on with it. But the idea basically is you shouldn't need to look at anything apart from this main.py file. At the beginning, it sort of sets out things like the interaction strength, the hopping strength, the cutoff for being diagonal, the disorder strength, some properties of the numerical integration. Yeah, it does a whole bunch of different things here. And then ideally, you should never have to look at anything that occurs below these lines, and it should just output you a file that has the diagonal Hamiltonian, the eigenvalues if the system is small enough, the ED eigenvalues as well if the system is small enough. It'll compute things like the L-bit interactions, it'll compute the L-bits themselves. It will compute the flow invariant, but I'm not certain the public version here does that correctly. I don't remember. I've not updated this for a few months. It can also do some dynamics, so it can compute things like the imbalance or just the dynamics of a single density operator, like a single local operator on one site. So it's not super user-friendly. So I'd say if you want to run anything that's kind of non-trivial, best to get in touch with me and ask me how to do it. The GPU stuff is contained in this folder here, TFE JAX. There's also a version using PyFlow, but that's much, much slower. I'm not using this anymore. The JAX version is the one I'm currently using. The structure is again basically the same as before. The main difference is that all the tensor contractions run on the GPU. Instead of using NumPy, I don't think this shouldn't use NumPy anywhere. Yeah, it uses jax.numpy instead of NumPy itself most of the time, because JAX creates everything directly on the GPU, and that makes everything much, much faster. So yeah, I would say you can run some basic things with this. Other people in the group here have managed to run this without me, but I would very much like to make this a bit more user-friendly, because at the moment I think it's kind of a mess for anyone who isn't me.
Oh, it's already looking great. So I think one question I will think about is, for example, you're updating the generator a lot, but for this quantum computing proposal, it's very relevant that you try to use an initial bracket and then continue with that for a bit and then switch again and so on. So that would be just a matter of modifying something in those main.py scripts, probably downstairs a bit because it would be the other applications, but
yeah, I mean it's very possible. It's reasonably straightforward to do that sort of thing actually. So it's not in the public library at the moment, but I have been playing with a slightly different version of the code that does exactly what you are mentioning. Well, not exactly, but does something very similar to what you're mentioning. So I've been playing with different choices of generator. This is new and unpublished, but I've been doing this thing where at the gray lines here, I change the generator depending on the particular problem. So the Wegner generator has some problems. It doesn't always work. For example, in a case where I have no diagonal elements to begin with, right? If my Hamiltonian is just the hopping, okay, we can solve this with a Fourier transform, but just as an example, if the Hamiltonian is non-interacting and only has hopping terms, the Wegner generator doesn't do anything. The generator is actually the identity. Or well, rather the unitary is the identity, and it can't diagonalize the problem. So this is the flow of the Hamiltonian with different choices of generator. Wegner doesn't work. This other one called Toda does work. And I've been playing with this adaptive thing at the moment, which does kind of what you're suggesting, that at certain points in the flow, it can change the generator to better suit the problem. So this version starts off by using a modified version of Toda to get the flow started. and then it kind of progressively becomes more and more like the Wegner generator as the flow goes on. It has some nice properties. Like, for example, if you take a random system, the Toda flow is very, very noisy up here, and it doesn't actually properly converge. Wegner does, but Wegner can have problems in the interacting case. So then I have this adaptive thing that, yeah, every I don't know what it is, when L is like 1 or 2 or something, it just updates the generator according to whatever properties I want it to have. So yeah, what you're mentioning there, that's I think relatively simple to do.
Yeah, I was just thinking about some simple ideas, like just to try out. Yeah, but I think in general what you are working on is quite also relevant and has also overlaps with like this huge amount of work on variational parameterized circuits and so on, because there people really think about what kind of choices that generators to choose, and here it's more like physics inspired to just take some ideas, right?
Yeah, definitely. But as I say, I think the choice of generator here, I mean, people kind of default to things like Wegner because there's a lot of literature about it and it's numerically robust, but it's not necessarily the best. I mean, there are some kind of more rigorous calculations that say by certain definitions, it is a very efficient choice. I don't know the details of those. I'm not sure they've ever even been published. But yeah, I think it very much depends on what your problem is. And I think my feeling is that we can probably do better than the Wegner generator for this purely numerical type approach, because this started with people writing these equations down analytically, right? You were trying to solve the fixed point Hamiltonian analytically to get an approximate model that you could do something with analytically. Now, the way I'm doing this is almost purely numerical, and then there's no reason that I have to stick to these generators that maybe have nice analytical properties. Now I think what I really need are generators that have nice numerical properties, and this is something I think people haven't really looked into. So yeah, I don't know so much about the variational quantum circuit stuff, but if there's anything from there that we could take to make these generators more efficient or physically better in any way, that would be great, because I think there's a lot of room for improvement here.
Yeah, at least I think in that field you have already some knowledge on like how to discuss the methodology and how to compare pears and apples and so on. It's like yeah, maybe later we can speak some I would be really interested about like this optimality of Wegner flow, and so maybe yeah. Harshang, do you have some more questions? I think we've seen the code now. So on my side, I think I'm quite a happy yellow duck.
Yeah, so we should continue.
So I
Or we
switch
should-
off now, and
Sure.
thanks, Steven, for this wonderful tutorial.
You're welcome.
Oh,
Thank
okay.
you.